So it looks like we've got another right on the hour people jumping on. That's great. So we'll give everybody another minute or two to pop in before we get started on the seminar. Just a quick announcement to everybody logging on for today's seminar. Our next scheduled seminar, it's not posted on the website yet, but just so you're all aware, the next one will be on Wednesday, April 19th at 2 p.m. And it will be on zeta potential and microrheology measurements using dynamic light scattering. The speaker will be Anna Morphesis from Malvern Para-Analytical. So we will get this posted to our website soon, and you will see an announcement over the next several days with the details of the seminar. But just so you are all aware. So with that, it looks like we're starting to stabilize in the number of participants that we've got logged in. I am pleased to introduce today Ericka Hachmeister, and Ericka is coming to us from Marks International, and she's going to be presenting on the analysis of volatile organics using thermal desorption, GCMS, which is very relevant as we have one of these systems in ARC in the chemistry building. So Ericka has over 10 years of experience in organic surface and compositional analysis with a heavy focus on VOC, volatile organic carbon analysis by thermal desorption. In preparation for her introduction, I actually asked her if she had anything else that she wanted me to add, and there was a wonderful anecdote that she provided. She is actually serving as a guide for a blind triathlete and is in training, not just for any race, but for the 2024 Paris Paralympics. So that was too interesting a nugget to pass up on. So I'm pleased to introduce Ericka, and I'm excited to hear her talk. And please feel free to ask questions at the end. Thanks, Ericka.
Yeah, Corey, thank you so much for that introduction. I will go ahead and dive right in. The goal of this presentation today is to hopefully familiarize you with Marks in general and our platforms, but then we'll take a pretty specific focus on what you have available to you in the chemistry building through ARC. So with that, we'll go ahead and jump right in with a little introduction. Since 1997, Marks International has been at the forefront of innovations for enhancing the measurement of trace-level volatile and semi-volatile organic compounds. So that's VOCs and SVOCs by gas chromatography. Our comprehensive portfolio of thermal desorption products includes instruments such as our Unity XR and our TD100 XR, as well as a wide range of high-quality sorbent tubes and innovative accessories that allow for the representative vapor profiling to be collected with minimal inconvenience. Marks is headquartered in Bridgend, Wales, and we also have laboratories and demonstration facilities in the US. I'm coming at you from our Sacramento lab, as well as Germany and China. So with that, let's dive into thermal desorption. So what is thermal desorption? Well, thermal desorption, or TD, as commonly referenced, is a simple multi-step process for the sampling and pre-concentration of very volatile to semi-volatile organic compounds. This can be from solids, liquids, or gases, prior to injecting and analysis by gas chromatography. The first step involves collecting the sample. This can be done in the field onto sorbent tubes using sorbative extraction probes, or even into a canister. Alternatively, samples can be collected directly in the instrument by online sampling or direct desorption and dynamic headspace. The analytes are then concentrated on our electronically cooled focusing trap that is sorbent packed, which is then rapidly heated in the flow of carrier gas to release the analytes in a gaseous phase and transfer them to the GC column in a narrow band of vapor. One of the major benefits to thermal desorption is it's a natural sensitivity boost, which can have an overall concentrating effect of up to 10 to the 6. This means that an air sample of hundreds of liters can be collected onto a sorbent tube, and then it is concentrated into hundreds of milliliters onto our focusing trap during the first stage of desorption, which is then further concentrated during the second stage of desorption into a few hundred microliters prior to injection onto that GC column. We'll talk more about that two-stage desorption. Thermal desorption is not just for air samples, however. It is often utilized for the analysis of both solids and liquid matrices. It is a faster and cleaner alternative to solvent extractions because there is very little or even no sample preparation involved. So there are several methods for sample collection for thermal desorption. Samples can be collected onto sorbent-packed tubes in a number of ways. It's pumped sampling, which is when sample gas is actively drawn through the sorbent tube using a pump. Compounds of interest are retained on the sorbent, and permanent gases pass through unretained. Then there's passive sampling. Passive sampling is when the compounds are diffusively sampled onto the sorbent tube, usually over an extended period of time. And then there's also direct desorption, which is available through placing solid samples into sealed chambers, which can then be heated and admitted compounds transferred onto sorbent tubes and then added to the thermal desorber for desorption. The great characteristic of sorbent tubes are that they are small and lightweight, which means that they're very easy to transport. They're reusable with sorbent suitable for hundreds of thermal cycles, and they can be really great for the volatility ranges from C3 all the way up to C44, dependent on your sorbent selection, which is another thing we will talk more about. When not using sorbent tubes, whole air samples can be collected into a canister or a bag and brought back to the lab where the air sample is then concentrated onto the focusing trap. Canisters are considerably larger than sorbent tubes, but they do allow for that capturing of the ultra-volatile C2 and have a range from C2 up to C12. Additionally, you can monitor in situ with online air samples, which are collected and concentrated directly onto the focusing trap. This method extends the range from those ultra-volatile C2 up to C14 because we don't worry about the C12s and C14s condensing on canisters. An additional sampling method is where a small amount of solid or liquid sample is placed directly into an empty TD tube and heated in the flow of gas within the instrument. The emitted compounds are again transferred and concentrated onto the focusing trap before injection onto the GC. Direct desorption combines sample preparation and extraction, pre-concentration, and a matrix-free injection in one labor-saving and fully automated process. In many cases, thermal desorption and direct desorption significantly reduce and simplify the sample preparation workflow. Many air, water, and soil sampling protocols involve filtering samples, after which there can still be several lengthy and time-consuming preparation steps involving solvent extraction of the sample. Simply placing the filter into an empty TD tube at this stage removes the large section of workflow, allowing it to be fully automated, solvent-free, which is more environmentally friendly. And additionally, direct thermal desorption can save some of the more volatile compounds that can be lost during solvent washing and drying, so the analysis of the filter can give a more representative picture of the sample itself across the volatility range. This kind of technique is growing in popularity for particulate matter analysis from air, and most recently in the rapidly emerging microplastic sector, where we're able to use this technique for both air, water, and soil samples. Other examples of TD of where TD simplifies the workflow include food packaging, food and drink profiling, consumer products, building materials, and even arson debris, and many more. So now that we've oriented you a little bit to what TD is, let's take a deeper dive into how it actually works. So we're going to talk about how it works mechanically. And as I mentioned, there's a two-stage desorption that we implement. Here, we're going to highlight the first stage for tube desorption, in which sample tubes are heated in a reverse flow of inert carrier gas to release the retained compounds and transfer them onto a narrow bore focusing trap. On all of Mark's tube-based systems, there's an option for an inlet split during the stage so that you can further, which you can either send to vent, or if you would like to recollect it for later use, you can do that as well. So alternatively to a tube, we can do online sampling, in which case the first stage is just to sample directly from the online canister or bag onto the cryo-cooled, I'm sorry, the electrically cooled focusing trap using controlled flows. So following this, during stage 2, the sample that has been focused and concentrated onto that trap is then rapidly heated at rates of up to 100 degrees C per second in the reverse flow of carrier gas. The compounds are released from the trap and injected onto the GC in a narrow band of vapors, providing sharp chromatographic peaks. On all Mark's instruments, included our online and our canister, there is an option for an outlet split during this stage, which can either be sent to the vent if not required, or recollected for later use. This slide provides information on what can be analyzed using thermal desorption, which is essentially any organic compounds more volatile than C44, which is also readily compatible with GC analysis. Most permanent gases are not going to be compatible with thermal desorption, except for the few you see on the bottom of the left side. So we're going to quickly just cover our sampling techniques that are available through Marks. Those are going to be tubes, canisters, bags, and online. So online and canister sampling have similar analyte ranges, but there are specific use cases scenarios for each, which we will cover briefly. Sorbent tubes have a far greater range than both, but lack the very volatile capabilities of online and canister-based options. If you think about the sampling environment where tubes are used, it is usually at or around room temperature. We can use the same sorbents in a tube that we can use in our focusing trap that can trap the ethanes, ethylenes, and acetylenes of this world. But in a trap, the temperature can be reduced down to -30°C to make it viable, whereas a tube used at room temperature cannot sufficiently trap them, and they break through the sorbents, which is something else we will cover. So when thinking about our sampling technique, oftentimes we first question sorbent tubes or canisters. So let's take a look of when we would elect to use sorbent tubes. When our compound range is from C3 to C44, if we're looking at short-term or long-term monitoring, and if we would be interested in taking passive, pumped, or chambered samples, of which we'll talk more about. And then also, sorbent tubes can be really helpful for a time-weighted average sampling study. We're not going to be able to use sorbent tubes for compounds more volatile than C3, just because we don't have strong enough sorbents to capture them at ambient temperatures. And then we'll dive more into sorbent materials, but it's really important that we match our sorbent with our analytes of interest, and sometimes this can present some unexpected challenges. So the reason we would pick a canister is if we were focused on ultra volatiles to volatiles, C2 to C14. And then it's also very effective for rapid transfer of ultra-volatile reactive compounds such as H2S. And then the canisters are also really great for simple grab sampling. An evacuated canister can very rapidly pull in a fairly large sample in a near instant. We're not going to use a canister for when we have less volatile compounds, getting above the C10, C12 range. High concentration of samples are going to permanently contaminate our canisters, so we would avoid that. And then it is not very easy to do time-weighted studies using canisters. And then we have our third option of the use of online sampling. So the opportunities that we would look to this is, again, when we have the C2 to C14 compounds, because we've eliminated canisters and we don't have to worry about compound condensation on the inside of the canister wall, we can extend that range to the C14. And then online sampling is really common for continuous monitoring, such as the PAMS method, if you're familiar with that, where we might take a sample for 20 minutes, analyze it for 40, and then do that at the top of every hour. It's also an in situ monitoring and can be used in multiple sources. It's got, when paired with our Cori system, it's got really powerful water removal to help protect your focusing trap and your GC. And then it's really great for those ultravolatiles and reactive compounds. Times we would not use it is if we're interested in compounds greater than C12 or C14, really. And then it does require in situ GCMS analysis. So wherever you are taking your sample, you must have your instrument, your thermal desorber plus your GC plus your detector. So if that's not possible, then online sampling isn't going to be for you. So that was a big overview, rapid fire, my apologies, of the platforms that Marks has and the different sampling capabilities that you can implement with them. What you all have available to you, the ARC, is a Unity XR attached to an Ultra XR. That Unity XR is our thermal desorber, so that's where the focusing trap is going to be held. And then next to it, that big tall tower with the black and clear door on it is going to be your tube auto sampler, 100 tube capacity for sorbent tubes or empty tubes that can be used for direct desorption. So from here on out, we're just going to talk about tube-based analysis, and I'm going to walk through sorbents and then some applications, or sorbents, sampling, and then applications. All right, so first we're going to talk about sorbents, and please do forgive my image of graphene there. Sometimes a pretty picture wins out over accuracy. And so first, let's talk about some of the key principles for sorbent selection. The biggest thing is that the sorbent used must quantitatively retain the compounds of interest from the volume of air or gas you're going to sample. And then it must be able to release those compounds as efficiently as possible during the desorption process. If it can't retain it or if it can't release it, you don't have a good match. Sorbent selection principally depends on the volatility of the analytes concerned. The more volatile your analytes to be trapped, the stronger the sorbent must be. And then these sorbents are generally broken up into three common classes: porous polymer, graphitized carbon, and the molecular sieve, or carbonized molecular sieve. So we're going to look closer into some of this. First, generally when we think of sorbents, we consider a number of characteristics. And you have those 5 in front of you. The first characteristic is the strength of the sorbent. Generally, the strength of the sorbent is broken down into weak, medium, and strong, with weak sorbents being able to capture volatiles, or ideal for volatiles with boiling points above 100 degrees C. For medium sorbents, we're going to look at the boiling point range from 30 to 100 degrees C. This is going to be something like a graphitized or a carbon 1TD. And then for boiling points, -30 to 50, we're going to use a strong sorbent. And these are going to be our molecular sieves, such as a carbograph 5TD or carboxyn. Sorry, the carbograph wasn't a molecular sieve, but then the next thing we're going to consider is the thermal stability. The thermal stability of the sorbent is going to dictate your maximum desorption temperature. The porous polymers are the ones you really have to think about here. Something like 10x TA is going to have a max desorption temperature or a max operating temperature of 320. And to reduce artifacts and to prolong the life of 10x, we generally only take it up to 280 or maybe 300. But something like a graphitized carbon black or molecular sieve, we're going to be able to heat those up to 400 repeatedly without causing any breakdown. The next thing we want to think about is inertness. Some sorbents are entirely inert, such as our porous polymers, the example of 10x. And then a number of molecular sieves, such as sulficarb. These compounds are really great for the analysis of thermally labile or reactive compounds, such as mercaptans. Sulfur-containing species, sulfurous pesticides, and monoterpenes. But something like a graphitized carbon is likely to contain trace levels of metal, which is going to make them reactive with these specific classes of compounds. So we want to avoid those. Next, we want to think about the hydrophobicity of our sorbent. Some sorbents are very hydrophobic and therefore useful when sampling in humid conditions, while others are extremely hydrophilic and will collect water sometimes in the milligram range during sampling. And this water really has to be managed during this normal desorption process to protect your focusing trap, your column, and your detector. The last characteristic we really want to think about is artifact levels. Graphitized carbon and our molecular sieves, once well conditioned or fully conditioned, they're going to have very minimal artifacts. But our porous polymers, especially our 10x TA, is going to at first exhibit low-level artifacts, primarily benzene and siloxane. And over time, it's going to continue to break down, and you will see that those artifact levels come higher and higher. So when selecting a sorbent for benzene analysis, if we need to be in the sub-nanogram range, we're not going to select something containing 10x because it will interfere with that analysis. All right, and I know you guys memorized all of that, so we'll be good to go. Just jump in a little bit more to look specifically at porous polymers. Again, we talked about they're great because they're hydrophobic and they're inert. They're not so great because they have artifacts and they have a low maximum desorption temperature. That second class was that graphitized carbon black sorbents. They're really great because minimal artifacts, which makes them suitable for trace level analysis of all compounds. They're fairly hydrophobic, so they can do all right in humid conditions. And they're generally non-porous, though some do exhibit some microporosity, which gives them an even greater range and volatility down to those ultravolatiles. But again, they're not inert, and they can be friable upon mechanical shock. And then our third class, those molecular sieve sorbents, these are our strongest compounds, and we're going to reach for them when we're looking for our most volatile analytes. And they're really excellent because they have those minimum artifacts, and they have generally a good level of inertness. They unfortunately love water, so generically speaking, they're not going to be very hydrophobic. In fact, they're going to be quite hydrophilic. We do need to protect them because they can become contaminated with some of those higher boiling compounds because they are so strong. And in a simple table, I give you your sorbent selection. So we have some of the most common sorbents here. You can see our volatility range is descending, as well as our, and then our increasing water retention comes down as our volatility range descends. So you can see quartz wool or beads they're just going to capture those really high boiling point compounds, and they're not going to capture any water. But as we move down finally into that carbosieve S3, it's got really great strength to it for ultra volatiles, but it's also going to grab a hold of all of our water. So what if we have a wide range of compounds that we want to trap and analyze? Well, that's a really good question, and I'm glad you asked. The answer is to use sorbent beds, to use multiple sorbent beds in a single tube. You can see here a representation of a glass tube with 3 different types of sorbents in it. On the left side, we have which is our sampling direction. We have our weakest, in the middle, our medium strength sorbent, and then on the right-hand side, or the picture diagram on the bottom, we have our strongest sorbent. We always want our sample to come in through our weak sorbent first, so that way the high boiling point compounds get trapped immediately, and the low boiling compounds pass through to our strong sorbent. The mark system has what's called backflushing in the focusing trap. So our focusing trap works the exact same, and that's why we sample in one direction and desorb in the opposite direction. So those high boiling point compounds never have to make it all the way through. They only get in as far as they want to. They're retained quantitatively, and then they leave in the direction they came. So luckily at Marx, we've done the work to develop some of these sorbent combinations. I'm not going to talk about all of these, just to give you an idea. You can look there at the second bullet point, universal tubes. This is a porous polymer, graphitized carbon, and a molecular sieve. This gives us a huge volatility range from C2/C3 up to C32. And then from what we've just learned, we know that this could potentially have some artifacts with benzene and siloxanes because of the porous polymer, and we know that it could hold on to some water because of that molecular sieve. So we're not going to want to take it to really high temperatures, and we're not going to want to use it in really humid environments. So I've got another page for you, and then again, you can just kind of look. We've got that hydrophobic tube, so porous polymer and a carbon black, leaving out the molecular sieve, giving us a volatility range of C6 to C30, but we can confidently use this in a much more humid environment. And all of these tube types are available on our website if you want to look closer. And like I mentioned, the same principles from sorbent tubes and sorbents there apply to our focusing trap. We, again, have a sampling direction and a desorption direction. The narrow design allows for a splitless injection. You're able to match your sorbent to your analytes of interest, and you can do that over a very wide range. We oftentimes recommend trying to match your cold trap sorbent materials to your sorbent tube materials. It doesn't have to be that way, but generally that's how you get the best results. And then at Marks, we offer now, I believe it's 24 standard traps, and then we have the capability to make custom traps and tubes based on if you have a unique application or interest. All right, we're going to take a closer look at tube-based sampling now. First, we'll start with just an outline of our tubes. All of our tubes and our instruments, and the instrument you have sitting in your lab now works on industry standard tubes, which are 3.5 inches long with a 1/4 inch ID. Each tube has a unique code with the possibility of adding custom etching if you wanted. The grooved end on your tube, which you can see circled in purple here, is going to be the sampling end. That's where your flow comes into and then your desorption leaves out of. And again, that will help. You'll know that your weaker sorbent, if you have multiple sorbent in a single tube, your weak sorbent is going to be on that notched end. Your strong sorbent is going to be on the opposite end. And then using these tubes, we can engage in 3 types of sampling methods, which is going to be passive, active, and direct sampling. So we'll dive into those a little bit deeper now. So for passive or diffusive sampling, the first thing to note is that this needs to be a single sorbent tube. You can't have multiple sorbents in there. And that's because for diffusive sampling, you require uptake rates. And among those uptake rates also requires a set air gap. And you can see here that we have a small diffusion cap that you apply to the top of your tube to set that air gap. So that way all uptake rates apply. And all of our tubes are made to that stringent 3.5-inch long, 1/4-inch ID. So that way published uptake rates will always apply to our tubes. It's important to note that diffusive sampling is a relatively slow process, typically taking multiple days. When we want to back calculate the concentration that we've detected on our tube, we're going to take the mass on tube of compounds in nanograms, divide that by the published uptake rate or established uptake rate, multiply that by our sampling time in minutes. Many uptake rates are available. It is specific to analyte on a specific sorbent. We are in the process of updating Mark's application note 1 to include more uptake rates, and that should be coming out shortly. There's a pretty big study coming out of the UK on that. And then if an uptake rate is not available for an analyte and a sorbent that you have interest for, it is possible to determine this experimentally, but quite difficult. It involves collecting several diffusive and pumped samples in the same quote unquote environment or atmosphere. And then you are able to use your pumped samples to provide you with a known concentration so that you can then calculate the uptake rate for the diffusive sampler. Lastly, for passive sampling, we have 2 types that are used. One is that tube-based, which is an axial sampler. Uptake rates are quite slow with it. As mentioned, sometimes you'll use it for up to 2 weeks. And then the other type is the radial. The other type is the radial diffusive sampler, which uses sorbent cartridges. These are generally used for workplace monitoring, where you maybe only have 8 hours to collect a sample, and they have uptake rates of 50 to 100 times faster than the axial sampling. You will have to use uptake rates that are specific to these products, though. All right, so when might we want to use diffusive sampling? Again, if the compound has a validated uptake rate, the test environment is not contaminated with other high concentration compounds, as this will offer competitive uptake and can alter your results. If your sampling time is up to 8 hours for occupational, or 1 to 4 weeks for environmental, and this is just based on needing to get enough mass on tube to be above your LOD for the method. And then because we are limited to a single sorbent, the analytes of interest do need to have a similar volatility range. We're not going to be looking at passive sampling if we need multiple sorbents to hit our analyte range. If we're sampling someplace with a completely unknown atmosphere. And not likely to use it if there aren't any known uptake rates. So if you can't do passive sampling for whatever reason, or it doesn't fit your needs, then we would suggest active sampling using a pump. Pumped sampling onto sorbent tubes is a versatile option for simultaneous monitoring of multiple compounds, whether in the open air or contained within bell jars or sample bags and other headspace containers. The Mark's backflush technology allows tubes to be packed with multiple sorbent beds, widening the analyte range detectable in a single run. Generally, active sampling can occur between 20 to 200 mils per minute, though we have some customers using their own pumps at over 1 liter a minute, which is quite aggressive. active sampling is always fully quantitative because you know how much sample you've pulled in. With this, you just want to be careful. Sorry, I forgot I'm automated. With this, you just want to be careful not to exceed your breakthrough volume. So let's go ahead and talk a little bit more about breakthrough and what that is. So when we pull our air sample in, ideally all of our analytes of interest are retained on our sorbent and the permanent gases pass through. So that's that first tube on the top. What happens with breakthrough is that some of our analytes of interest also pass through the tube, and that can be either because our sorbent is not strong enough to retain them or because we've just sampled too high of a volume. Breakthrough can be affected by our sorbent type, our sample volume, our temperature during sampling, and the total mass of sorbent we have available. So we can test for breakthrough in generally two ways. The first of those two ways is to use two tubes in which you take samples of two different volumes. If there has been no breakthrough if the tube with the larger volume shows a representative increase in peak area. So in this example, that 4-liter sample would show an approximate 4 times the peak area of the 1-liter sample. And the other way we can do this is to put two tubes in series. For two tubes attached in series, the second tube in the series will remain blank until the sample volume reaches breakthrough volume. So if you know that you want to pull 6 liters through a sorbent tube at a specific location, you can go out there, do a few test runs with tubes in series. All 5 of your tests show you that you have no breakthrough for 6 liters of sample, then you can consider yourself safe at that volume. A way that an active pump can be implemented is to use our active sampling with the MTS32, which is a multi-tube sequential sampler. It's a low-emitting polymer box with a polycarbonate water-resistant airtight lid that you can load up to 32 tubes in it and just leave it in the field. You press go and then you come back and get it after sampling has been completed. This offers unattended sampling for, like I said, up to 32 tubes. How it works is that it allows air to be pulled sequentially through standard tubes using consistent flow pump technology. The constant flow allows for the sample flow rate and overall total volume to be the same across all of the tubes, despite impedance variations over sampling durations. Your sampling times can range from 1 minute up to 99 hours, but it does have to be the same sampling time on each tube. And then for this application, you can actually use flows as low as 5 mils per minute up to 100 mils per minute. So you could take this out, set it at a landfill site, or in a forest and collect, 32 1-hour samples to get a time-resolved study of the VOCs in that area. Next up is direct desorption, which is a highly effective way of sampling organic vapors from homogeneous materials containing relatively high concentrations of volatiles. With direct desorption, a small quantity of a material is placed in an empty TD tube, and the tube placed in the thermal desorber. It is then gently heated and the flow of inert gas to dynamically extract headspace volatiles directly onto the focusing trap. So sometimes that we would think to use direct desorption is if we have a solid sample. We can also use it if for a majority of liquid, gel, or paste, you're going to reach for direct desorption in an empty tube when you would rather weigh out your liquid than do it by volume. So something with a little bit of viscosity to it, or maybe a little bit of stickiness to it. You're going to reach for this if you are interested in looking at emissions or odors. And it's going to need that the sample can be heated to release those SVOCs or VOCs. And we also want to make sure that we're using homogeneous samples here because if our sample is inhomogeneous, because of the small amount we're using, we could misrepresent it, and that will result in some poor reproducibility. And then lastly, you just want to note that if you're putting some plastic pellets in there or something that can melt, you can damage your system if you overheat it by melting something and coating the inside of your instrument. So it is important that you use caution when using direct desorption. Oftentimes, we're just trying to heat it warm enough to get the volatiles out, but not really to fully disintegrate whatever we're looking at. Or going back to sorbents, but still talking about like bigger samples or solid samples, the microchamber thermal extractor is a compact standalone device that can be used for rapid sampling of chemicals, odors, and released from a variety of products, foods, and materials. It also allows for reliable unattended sample preparation prior to TD or HPLC. We'll touch a little bit more on that. Actually, I think I took that slide out. I'll just comment that HPLC, the microchamber is compatible with DNPH cartridges that can be used to collect formaldehyde from solid samples, and then those can be derivatized and run using HPLC. So then just a quick look at the ease of use with the microchamber. Again, there are these nice little sample cups. You stick your sample in it, you close the lid, you set your conditions, time and temperature. You affix your tube and you press go. You remove your tube, place it in your instrument, and analyze it with TD-GC-MS. Times that we would want to look at using the microchambers, again, if we have solid samples, if we want to look for those emissions and odors, samples need to be heated in order to release VOCs and SVOCs. And here, because we're able to use a much larger sample size, it's okay if the sample isn't homogeneous, as long as over a larger scale, you're able to account for all of the inhomogeneity of it. And again, it's also compatible with those DNPH cartridges for formaldehyde analysis by HPLC. Here we have a comment that it's not compatible with liquid, but it actually is. We came out with an insert that will allow you to do liquid. It's just that if you have a liquid that's going to volatilize rapidly, it doesn't give you enough time to load the chamber and close the lid before it volatilizes. So you'll be limited on those ultra volatiles there. And you're also a little limited on the SVOCs. The microchamber isn't compatible with anything much over C30, and that's just because it only goes up to 250 degrees. So that's going to be our limiting factor there. The last little bit, as we're talking about tube sampling, let's just touch quickly on how we want to handle our tubes. If we are going out into the field and we have tubes stored in our lunchbox, no, I'm just kidding, in our air-conditioned car, we want to make sure that when we bring those out into the environment, we let them come to ambient temperature, whatever that may be, to avoid any condensation that could affect our sampling or later our analysis. Once we've collected our samples, we can bring those back to the lab with storage caps on them. For a single sorbent bed, it's okay to just leave those sit nicely capped out on the bench top for up to a month. For multi-sorbent beds, if we're keeping them at room temperature, ideally we want to analyze that as soon as possible or within a week. This is just to reduce the risk of compounds diffusing from one sorbent to the next. If you need to store them for longer, you can totally do that. We're just going to recommend refrigeration or freezing. And it is important to note that they need to be properly capped. You put them into your refrigerator or your freezer, you let them come down to temperature, and then you retighten them because of the metal shrinkage. They'll become a little loose. And if you don't retighten them, you will begin to sample the inside of your freezer. And if you are doing weird beef studies in your freezer, then you'll sample a whole lot of beef samples as an example. And then when you're ready to analyze those samples, go and take them out, let them come back to room temperature again to avoid any condensation before removing the caps. The last bit about tube sampling that we'll talk about is the use of the tube conditioning TC20. This is something that I believe that you guys are hoping to add to your lab, and it's just to highlight that we can condition up to 20 tubes offline under the purge of clean, dry nitrogen at up to 400 degrees to eliminate the background of a dirty tube prior to taking it into the lab or uh, into the field for sampling. And you can see our black trace of an unconditioned 10x tube, and then the red trace of a 10x tube that has been conditioned for 2 hours at 320 degrees C, so it's max functioning temperature. All right, to the more exciting stuff, I think we're going to go ahead and kind of rapid fire some applications here that I hope will have a little bit of relevancy to what you all might be studying or thinking about, or at least help you see some ways that the Marks platform has been implemented and ways that you might be able to expand on in your own areas of research. So the first step, we'll just look at disease diagnosis. Breast sampling of VOCs has gained prominence as a potential useful approach in the early diagnosis of many diseases, as well as the study of VOCs with direct links to disease. An important aspect of research in this area involves investigating how other factors such as diet and environment may affect breath volatiles. As part of this effort, UK researchers have been using TDG-CMS to analyze the effects of stress on breath. So what you see here, the red dash is a participant of the study doing a stressful event, a mental arithmetic test, and then the blue solid line is that same participant listening to some relaxing music. And you can see that the apparent onset of stress has altered some of those detected VOCs in that participant's breath. Another thing that we can look at are skin volatiles. Skin volatiles are a major factor in determining the attractiveness of humans to mosquitoes and hence to the risk of exposure to diseases such as yellow fever and malaria. The attractiveness varies markedly between individuals and is not only determined by genetic differences, but also thought to be related to the presence of certain microorganisms on the skin. So what researchers did is they had participants rub their feet on some glass beads, and those glass beads were collected and desorbed using direct thermal desorption. And you can see here they've highlighted, for example, peak number 1 on the far left, compounds that may attract mosquitoes, and then peak number 7 on the far right, a compound that could repel mosquitoes. And researchers believe that this can have implications in helping to develop new malaria prevention strategies. So jumping into a different subject, ecosystem and the atmosphere. I have a couple of examples for you here. So monoterpenes dominate amongst the VOCs emitted from many plants and are consequently important in atmospheric chemistry. But some of these compounds are highly reactive and prone to rearrangement within TD analytical systems. The inertness and adjustable flow path temperatures of the MARCS TD system ensures reliable analysis of monoterpenes in addition to single run analysis of compounds from C2 to C44. The use of porous polymer sorbents such as 10X avoids on-tube decomposition of certain analytes, while inert coated stainless steel tubes are useful for the most reactive compounds, such as sulfur species. Validating recovery with these reactive species is made possible by the slitting and recollection capabilities of the MARC-TD system, which you guys have in your lab. So a quick look, many biological derived VOCs or BVOCs are very reactive and are oxidized in the upper atmosphere. into heavier molecules. These condense to form secondary organic aerosols, which is a growing area of interest currently, which can act as a cloud condensation nuclei. Understanding how BVOC emission from plants may change with rising temperatures is therefore necessary to shed light on the global climate feedback mechanism. So we have a team from the University of Copenhagen that was able to do in situ pumped sampling onto sorbent tubes using TD-GCMS analysis to study the long-term effects of different conditions upon BVOC emissions of Arctic heathland. For this application, the short growing season and remote location demanded the use of large number of sorbent tubes, making the on-tube stability of analytes and the ease of tube transport particularly advantageous. And you can just see here that they're identifying that over a 12-year period, there seems to be an increase in BVOCs by warming and to a lesser extent by leaf litter or just degrading leaves, causing significant alterations to the emission rates of certain mono and sesquiterpenes. All right, I'm getting there. I hope you guys are enjoying drinking from the hose, but some really interesting stuff with some chemical ecology. Here we have a study looking at the role of VOCs in multitrophic relationships. Research into the role of plant volatiles with entire species communities compromised promise to shed light on how evolutionary pressures have shaped the ability of plants to release VOCs. Interactions between species forming part of the food chain, trophic levels are a key aspect to the fascinating area. For example, the volatile profiles of many plants change substantially upon being eaten by herbivores, such as caterpillars, and in some cases, these modified profiles can then attract predators of those herbivores. Researchers in the Netherlands Institute of Ecology have pioneered work using the TD-GCMS. And here you can see that in the absence of visual cues, but with the emission of VOCs, we have an increased attraction of birds to infested trees. And when you eliminate the VOCs and you only have the visual cues, that change actually goes away, highlighting that the emitted VOCs from infested trees are bringing in the birds to help save them, to eliminate their pest. Next up is just a quick look understanding the effects of ozone on fluorovolatiles, as well as visual cues. Plants, like I said, can use volatiles released from the flowers to attract insects and so achieve pollination. Ozone, generated by the action of sunlight on air pollutants, may interfere with this process by reacting with certain components of the flower scent. A research group from Spain is investigating the potential impact of ozone by studying the volatile blends of flowers, or how the volatile blends of flowers change when treated with it. Using a continuous flow apparatus to control the reaction time, vapor phase mixtures were pumped onto sorbent tubes and analyzed using Mark's TD equipment. And you can see here just a couple of key points. The levels of monoterpenes in ozone-degraded blends were about 25% lower than those of unmodified, and those did affect the preference of the bees. I'm going to skip over this one. My apologies. Just one slide on emerging market. I thought you all might be interested in some of the PFAS in air study. Per and polyfluorinated alkyl substances, or PFAS, are a class of persistent organic pollutants that enter our environment through multiple industrial and everyday sources, including water-resistant coating, firefighting equipment, and non-stick cookware. They include a wide range of chemicals covering different volatilities, polarities, and functional groups, with recent reports citing over 6,000 compounds of potential interest. The current challenges for PFAS monitoring include the sheer number of potential compounds of interest, the low concentration, these compounds are typically in the sub-ppt, and the identity and level of compounds present in the environment are largely unknown. Importantly, this last point means that the unknown or non-targeted PFAS are often just as important to regulators and researchers as known targets. Whoops, I'm sorry. And now I lost it. So this is where TD-GCMS can come in. It can help with two groups of PFAS compounds. It can help us with looking at the very volatile perfluorinated hydrocarbons from C1 to C3, also known as the potent greenhouse gases. And ozone depleting substances. This typically requires whole air sampling, so canisters and online. And then it can also help us with the volatile or semi-volatile PFAS species, such as perfluoryl carboxylic acids from C4 to C14, the fluorotelomere alcohols, the fluorotelomere acrylates, and fluorotelomere sulfonamides are all compatible with pumped sampling onto sorbent tubes. Trace PFAS in air is clearly a concern from a human health and environmental perspective, and the MARC system with TD GCMS can easily be applied to air monitoring for these trace level organic vapors. And that chromatogram is just highlighting a very wide range of PFAS compounds from the ultra-volatiles up to the semi-volatiles. And you have here single quad data using SIM analysis with the 131 master charge ratio. So hopefully that's all I've got to say. If you give me another hour, I'd talk for another hour. But I am part of your dedicated US-based support team. Again, your US application specialist in thermal desorption. Please feel free to reach out to me if you have any ideas, questions, need more information. I'm here to help you. Mark is also on this call, and he is located directly in your area. He's your field sales representative, also a chemist, and really understands the applications of thermal desorption from a user standpoint, as well as being able to help you with anything on the sales side of it. And with that, I will end here.
Thank you, Ericka. That was great. Let's open it up for questions. We have a couple of minutes left. The application on PFAS is interesting. When you've seen people doing that, what sort of sampling is it? Is it air sampling, water sampling, solids, soil contamination? What's the
Yeah.
range of samples that go in for that sort of analysis?
Yeah, so right now for PFAS and air, for PFAS, we are focusing on PFAS and air samples. That doesn't mean that you can't use soil samples and thermal desorption, and we're looking at sorbative extraction techniques for water samples, but we've primarily been looking at the ultravolatiles, even down to CF4, which is a byproduct of incineration of PFAS compounds. That's going to be a canister-based analysis. We're actually working closely with the EPA on establishing an OTM 50 method to move forward with the monitoring and putting criteria around that CF4 compound. And then on tubes, a little bit bigger than that, of course, but all the way up to about that C14 range. So really covering the ultra volatiles up to volatiles and maybe even a little semi-volatile. Yeah.
Other questions?
Hi, Ericka. Thanks
Hi.
for the presentation. That was really great. I learned a lot.
Good, I'm glad.
I had a few questions though. So when it comes to determining the concentration of your compounds on the tube, how do you do that? Do you use some kind of standards? How do you sample for
Oh,
that?
yeah, excellent question. Yep, so essentially a pump sample, you can quote unquote say that you're quantitative, but of course you do need to do some sort of quantitation on your GCMS system using TD. So we do have a device. I'm not sure if you have it available to you in the ARC, but our calibration standard loading rig, which enables you to inject a liquid standard onto a sorbent tube. Generally, that's half microliter up to 3 microliters. In methanol is ideal, but not necessary. You inject that at ambient temperature under the flow of an inert gas, and then we recommend purging off as much of the solvent as possible. You can also inject gaseous standards if you need to. And then some systems even have the ability to do internal standard injection from a gas directly into the instrument. And then you would, we generally don't recommend making one standard and injecting multiple tubes at different injection volumes, but rather making maybe 5 different standard preps and injecting 1 microliter of each of them onto 5 different tubes, and then running those to get your calibration curve.
That makes sense. Thank you.
Yeah, you bet.
Caroline with a raised hand.
Yeah. Hi, Erica. Thanks so much.
Hi.
It was a really interesting talk. Hey, I was curious if you've seen anybody. We have a TGA system here in the facility as well, where we do thermogravimetric analysis just to follow the weight change, when you're heating up a sample, which gives you some indication of materials changes, decomposition, water coming off, volatiles coming up. Are there any applications where you could see this connected to the outlet of these systems? I know some people hook up a mass spec or an FTIR to those systems, but I'm just wondering if there's a way to collect it onto a tube and not having to buy another detector on a system that we have here currently.
Yeah, so we don't have any application notes about that, but and it's just interesting because it's really just in situations like where you are, where people have access to all those different instrumentations and they're interested in learning that. We have heard it come up a couple of times in my life before Mark's. I did get to connect a mass spec and ultimately like a carbon packed sorbent tube onto a TGA to do a little bit of analysis. It can be a little tricky, but I do think that it's something that's more than possible. You really want to make sure that you can control the flow of that exhaust that you're sampling. But otherwise, it's just like sampling any exhaust. You will, of course, if you're volatilizing very large compounds, they might permanently absorb to your sorbent. So that would be a concern. So just making sure that you're the temperatures you're going to volatilize those compounds aren't too high such that you're generating compounds that won't come off your sorbent.
I have one more question. So, we sometimes see people with a piece of polymer or something, they want to just see what's coming off. Maybe there's a weird volatile that's coming off in their, while they're synthesizing these materials. And so far we just have used them, by SPME or, stick it in a vial, collect it on a SPME syringe. Or when would you actually go this route? Like, is it more if you have lots of samples and you have an auto sampler and you can collect multiple samples at once, or is there still a benefit to maybe going a SPME route or headspace route versus a full TB workflow? Because I didn't know you had these little tubes where you could stuff a piece in, basically. Yeah.
Yeah, so for me, like I would gravitate towards always trying TD first, primarily because, like the SPME and the different PDMS materials, you gotta get them clean, you gotta worry about background. But for an empty tube, you just, like you bake your empty tube out a little bit, you stick your solid sample in, you take your mass of it, and then you thermally desorb it. The thing is that for SPME, they're going to be a bit selective in the compounds that they're going to retain, right? So you kind of, you're only going to get what you're looking for. In that sense, so with direct thermal desorption, you could get anything and it could potentially cause an issue on your instrument. That's where you're going to want to be really patient and maybe run a few samples starting at lower temperatures, higher splits, do a little bit of investigation rather than just starting off with, 5 megs of samples at 300 degrees. You could really shoot yourself in the foot there.
Yeah.
But I think that by way of exploratory and unknown, TD is really great and is going to have a leg up over that SPME or other sorptive extractive technique.
Okay. Good, thanks.
Yeah, you bet.
Other questions? Well, thank you again, Ericka, and thanks for joining, Mark, and we appreciate your contributions today. We will get this recording posted, and we'll actually let you know where it is as well so that you can reference it, and if you want a copy of it, we can certainly send it to you.
Great. Thank you so much for having me, and I appreciate everyone's time and attention today.
And thank everybody for attending.
Thank you.
Excellent. Thanks so much. Appreciate your time. Have a good afternoon.
Bye.
Bye all.
All right.